Dear students, in this section we are going to discuss the cases of lens with different media on either side. Suppose one situation. Suppose we have a thin lens made of material having refractive index mu. Suppose this thin lens is placed in air. That means refractive index all around is mu equal to 1. Now an object is placed in front of this lens at a distance u from lens, right? This is the object distance with respect to lens. The image of this object after refraction through this lens form on the right hand side at position capital I. This is the image position. Suppose distance of the image from the object is v, and if we are interested to find the value of v, we use the lens formula. If we know the focal length of this lens, we can find the position of the image, that is value of v, by using this formula. This formula is called the lens formula. Remember this, the lens formula, this lens formula is applicable only when the medium on the left hand side and right side of the lens is same. But what happens if the medium on the left hand side and right hand side differ? Suppose medium on the left hand side is mu1 and medium on the right hand side is mu2. In that case, we cannot use this formula because this formula is applicable only when the medium on the both sides is same. But in this particular case, medium on the both sides is different. That means we need to consider first refraction through this curved surface, then image formed by this curved surface will act as the object for this surface. Again, we need to consider the refraction through this second surface, and finally we can find the image position. And we know the refraction through the curved surface. Suppose we have the curved surface having the radius of curvature capital R, and refractive index on the left side of this curved surface is mu1 and right side of this curved surface is mu2. The object distance is u and image distance is v. In this particular case, u and v are related by this formula, and we have learned this formula in the earlier section. Okay. So in our particular case, this is the first surface having the radius of curvature R1, and this is the second surface having radius of curvature R2. Okay. Now let us learn what is the meaning of mu1 and mu2. Mu1 is the refractive index of the medium from where ray is traveling before interacting with the curved surface, and mu2 is the refractive index of the medium where ray travel after refraction through the curved surface. So if we apply the curved surface formula for this surface, mu1 should be equal to mu1 and mu2 should be equal to mu, because after refraction through this curved surface, ray travel in this medium, and radius of curvature of this surface is R1. So for surface 1, we can write mu1 equal to mu1, mu2 equal to mu, and R equal to R1. And now we can substitute these values in this formula, right? So we can write like this. Now V1 is the image of the object formed by this surface, and the image formed by this surface will serve as the object for this surface. That means the object distance for this surface is V1, and let us consider the final image formed at V. That means the image distance should be V. And mu1, now consider what will be the value of mu1 and mu2. Mu1 will be equal to mu because ray before interacting with this curved surface traveling in this medium. So this is mu1, mu1 equal to mu, and mu2 equal to mu2, and radius of curvature of this surface is R2. So let us apply the curved surface formula for the surface number 2. Okay, and let us substitute the values in this formula. So this expression will become like this. Okay, now if we add these two, what will happen? This V1 mu divided by V1 and mu divided by V1 will get cancelled, and we have the final formula like this: mu2 divided by V minus mu1 divided by U equal to mu minus mu1 divided by R1 plus mu2 minus mu divided by R2, right? And mu1 means, again revise, mu1 is the refractive index of the medium where ray is traveling before interaction with the curved surface, and mu2 is the refractive index of the medium where ray is traveling after interacting with the curved surface, right? So here we can use this formula directly if we want to find the image position of this object. So up to this point we learn the theoretical part of this concept. Now let us learn the application of this concept, and here we are going to take few selected illustrations, and through coming illustration we will learn the application of this concept. So let us move to illustration number 1. In this illustration we are given a thin equiconvex lens of glass of refractive index mu equal to 3/2 and of focal length 0.3 meter 30 centimeter in air is sealed into an opening at one end of the tank filled with the water of refractive index mu equal to 4/3. You can observe here this is a tank filled with the water and refractive index of the water is 4/3, and this lens is fixed at this position. On the opposite side of the lens, here a mirror, plane mirror, this is a plane mirror, is placed inside the tank on the tank wall perpendicular to the lens axis as shown in the figure. You can observe the width of the tank is 0.8 meter and this plane mirror is installed at the vertical wall just in front of this lens. Okay. In next part of the question it is given the separation between the lens and mirror is 0.8 meter as shown in the figure. You can observe a small object is placed outside the tank. This is the small object. It is placed outside the tank in front of the lens at a distance 0.9 meter from the lens along the axis. That means the distance of this object from the lens is 90 centimeter. We need to find the position relative to the lens of the image of the object formed by the system. We need to find the position of the final image formed by the system, right? We need to find the image of this object, final image of the object formed by the system, right? So let us analyze the situation. Rays will start moving from the object interact with the lens. Then they move into the water and interact with the plane mirror, then come back again, interact with the lens and come finally, right? So here one more thing we can observe. This lens is placed on one side, left side of the lens there is air, and on the right hand side of the lens there is water. That means the lens is not having the same medium on the both side. That means lens maker formula is not applicable. That means we need to apply the concept which we learned here, this one. For this purpose we need to find the radius of curvature of the lens, and in the question we are given the equiconvex lens. That means the radius of curvature of the both side will be same, and this is having the refractive index 3/2 and focal length 0.3 meter in air. That means from the lens maker formula we can find the radius of curvature, and radius of curvature can be substituted here to get the image position formed by this lens. Okay, so let us first calculate the radius of curvature of this equiconvex lens. We know equiconvex means the radius of curvature on the both sides is same. Let this radius of curvature is small r. That is the magnitude of the radius of curvature of this side, and this side is small r. Now we can observe the center of curvature for this surface is on the right side and center of curvature for this surface is on the left side. This is surface 1, radius of curvature r1. This is the surface 2, radius of curvature r2, and here r1 is equal to r2. Okay, and we have the lens maker formula, this one, 1 upon f equal to mu minus 1, 1 upon r1 minus 1 upon r2. And in the question we are given the focal length 30 centimeter, and focal length of this length is plus 30 centimeter, and mu is given as 3/2. This is 3/2, right? And let us assume r1 is equal to r2 because it is equiconvex lens. So r1 and r2 equal to small r. The sign of the radius of curvature of the first surface will be positive because center of curvature will lie on the right hand side, and we are assuming positive direction is from left to right. So we can write here 1 upon small r minus 1 upon minus r, because center of curvature of this surface will be on the left hand side. So here we can write for this lens capital R1 equal to plus r, R2 equal to minus r, and mu equal to this one. So let us substitute this value. Now we can find the value of small r, that is 1 by 30 equal to, this is 1 by 2 and this is 2 by r. 2 and 2 will get cancelled. That means small r equal to 30 centimeter. So here we got the radius of curvature of this surface as well as this surface as 30 centimeter. Now let us consider the situation again. As we discussed, the medium on the left hand side and right hand side is different, and we know here is air, and this lens is having the refractive index 3 by 2, and here is the water, refractive index 4 by 3. And getting the image formed by lens of this object, we should use the formula this equal to mu2 divided by v minus mu1 divided by u equal to mu minus mu1 divided by r1 plus mu2 minus mu divided by r2. Here mu1 is the refractive index of the medium from where ray interact to the surface, just before interacting with the surface, mu1. So mu1 is equal to 1, and u here is equal to minus 90 centimeter, mu1 equal to 1, and mu2 is equal to this one 4 by 3, right? So here we can write mu2 equal to 4 by 3 and mu equal to 3 by 2. So now let us write u equal to minus 90 centimeter, u1 equal to 1, u2 equal to 4 by 3, and mu equal to 3 by 2, and unknown value is v. Suppose this v equal to v1. v1 is the image formed by this lens of this object when rays are traveling from left to right direction. So let us substitute the values in this formula. If we solve this, we can get the value of v, and v is equal to here 120 centimeter. This is v1. v1 equal to 120 centimeter. That means ray start from this position, interact with the lens and converge to this point, 120 centimeter from the lens, and we know this distance is 80 centimeter. So this should be 40 centimeter. Now we can observe these rays interact with the plane mirror, and you know this object, this image formed by the lens will act as the virtual object for the mirror. That means the image formed by the mirror should be in front of the mirror like this. This should be at the distance 40 centimeter. So this is 40 centimeter. Now you can observe rays are again interacting with the lens, and here the same situation. One side is having the refractive index 4 by 3, other side is having the refractive index 1. So let us apply the same formula, this one again, right? But in this case, mu1 should be equal to 4 by 3, mu2 is equal to 1, mu equal to 3 by 2, right? And we are assuming the positive direction from left to right. That means u value should be equal to from here to here. This is 40 centimeter. So here we can write u equal to plus 40, mu1 equal to 4 by 3, mu equal to 3 by 2, mu2 equal to 1, right? And here we are interested to calculate the value of v. Suppose v equal to v2. Now let us substitute the value, this one, and from this relation we can find the value of v2, and v2 is equal to 90 centimeter, and this is plus 90. Plus 90 means right side of the lens, and here is 80 centimeter. That means the final image, we can say final image form on the right side of the lens at the distance 90 centimeter from it. Okay.